There we go. Let's just try solving these equations, okay? Hopefully you can do the first one. So z squared equals 3 minus 4i. Can you tell me how to do it? But don't worry about actually doing it. So if I want to solve z squared equals 3 minus 4i, how do I actually solve that?
Well, I mean, so the margin square.
Exactly. Just take the square root of 3 minus 4i. We just did that. We just did loads of those in the last example. Okay, so I'm not going to make you do that now. Okay, on the basis that you should be able to do that now. Okay, if we look at question 2, so that was question 1. If we look at question 2, we have z to the power 4 minus 2z squared plus 4 equals 0. Let's have a go at this one. Okay, so has anybody got any ideas for how we could go about solving this one?
I know, quadratic, but I mean, it's just, there's no, I mean, unless z implies something, but there's
Yep.
no imaginary, there's no complex.
No, so z in this case is just a variable, okay?
It's a variable,
Yeah. By the way, you know, I tend to write all my complex numbers using z. That's just a convention, right? You can use any letter you like. You don't have to use z. So just because you see z in an exam or any kind of, you know, situation does not automatically mean it's to deal with complex numbers, right? In this case, I'm just using z to represent a variable. Now you say it's a quadratic. It's not quite quadratic because it's power 4. But yeah, it's a hidden quadratic. Fantastic. You notice this power and this power are related. This power is double this power. That's the kind of conditions for solving a quadratic equation or quadratic-like equation. So what I'll do is I'll let u equal z squared. And if I do that, I get u squared, because z to the power 4 is z squared to the power of 2, so that must be u to the power of 2, minus 2 times by u plus 4 equals 0. Happy with that?
Yeah.
Okay, so if I solve this equation then, you could try and faff around with factorising, but in this case actually, does it factorise? I don't think it does very easily. So I'm going to use the quadratic formula. Okay, so just remember, quadratic formula says, if I have a, in this case u, let's use u to be consistent, au squared plus bu plus c equals 0, then u must be equal to the negative of b plus or minus the square root of b squared minus 4ac all over 2a. Happy with that? Okay, so if I literally just stick in my a, b and c, well my a is 1, my b is negative 2 and my c is 4, I get 2 plus or minus the square root of 4 minus 16 all divided by 2. If I simplify that slightly, I get 2 plus or minus, that's going to be square root of negative 12, which I could write as square root of 12 lots of I. Happy with that? Because square root of negative 12, square root of 12 times I, yep. All divided by 2. Realising square root of 12 can be written as 2 root 3. I could write that as 2 plus or minus 2 root 3, lots of I, divided by 2. If I divide both of those terms by 2, are you happy I just get 1 plus or minus root 3i? Yeah? Now, of course, that's u.
Yeah.
That's not what I wanted. I wanted z, exactly. So knowing the fact that u equals z squared, let me just write it over here. I can say z squared is equal to 1 plus or minus root 3i. Well, okay, if I want z then, I'm going to have to take the square root. So actually, in this case, I'm going to separate it into plus root 3i and minus root 3i. It's two separate equations. So I can say z must be equal to the square root of 1 plus root 3i, or z must be equal to 1 minus root 3i. Okay, and realise, square root. Okay, well, I know how to take the square root of a complex number, right? So let's have a go at that. Okay, we've just about got time. Can you have a go at trying to take the square root of these complex numbers then? So convert them to polar form, then use de Moivre's theorem, find all the relevant roots, and then put it all together. Okay? Okay, so literally just applying De Moivre's theorem there, you should get those 4 answers. So if you just consider the 1 plus root 3 case, take the square root of that, just double check to make sure I have done that right, I think I have. And then doing this 1 minus root 3 case separately. So in each of those 2 cases, because you're taking the square root, you can use De Moivre's theorem, which gives you 2 roots this side, square root this side, 2 roots this side. And of course, realizing the fact that you wanted z originally, then actually it's just going to be all of these 4 numbers are valid. Okay? So in other words, any of those 4 numbers stuck into this equation here should give you 0. Okay? And again, thinking about the fundamental theorem of algebra, this is the order of the equation, 4. It's the highest power. How many solutions are we expecting? 4. Yeah, so it's a double check which you can do at the end to make sure you've got them all.
I was just wondering, when you displayed your gradients and the, you did it with the z squared, right?
Here.
No. Where there's r equal 2 and there's the pi divided by 3.
Yes.
Is that in relation with the z's?
Yeah, so these are related to the z's above. So
Z's above.
these are related to that one, and these are related to that one. So it's related to 1 minus root 3 and 1 plus root 3, right?
Yeah, it's just because there's a root 2.
Exactly. So the root over the top,
Yeah.
I do down here. So I've kind of done a few steps in ones.
Because I thought it was the one above.
No, absolutely. So this r and this theta are related to the number
Just
underneath the
inside.
square root. Exactly.
So,
Yeah. So this is the 1 plus root 3i, oops, root 3i, and this is the 1 minus root 3i. And then literally, because I'm fairly used to doing these in my head, but if you want to put more working down, then fine. I've literally just taken the square root of these 2 numbers. So I've taken the square root of 2, and then I've raised that to the, or times that by 1/2 to get pi by 6.
it's just because of the way you've written it.
Sure.
It wasn't that clear, and I wanted to make sure.
Fine. No, absolutely. No, that was my mistake. I should have written more working down, but yeah. Basically, these are your final answers. If you need to write more working down, fine, go for it.